Do example 4 here, which is another simulating without data. So creating your own data. This is from Alexander Demos. And their research question is kind of abstract. He just uses generic variables, asking if there's a difference in the dependent variable across conditions, controlling for subject and item. So this is what the model would look like. Dependent variable as a function of condition, which is a fixed effect, and then subject and item being random effects. So once again, we'll get data, create model, run model, and power curve. This is the R code, so there's a lot going on here, but we'll have to create our own data first, do modeling, simulate, and then a lot of work doing here on our power curve. So we'll turn over to the R code in RStudio. Here we add our R code. We will start by getting data. We're going to create our different variables. To start with, item, subject, and condition. And then we're going to expand that to create a frame for our data. We go here. And again, this is all from Alexander P. Demos. We're going to create fixed intercept and slope numbers for that. And then random intercept and slope variance covariance matrix. So that's what that's going to call it, and create a matrix here. That's for subject, and for items, we'll create another matrix, and then we'll get residual standard deviation. So now that we've kind of got all those numbers and iterations, we'll make our linear object. And so we see here dependent variable, it's a function of condition, and then subject and item as random effects, and then these different numbers within the different settings. So we'll run that, and then we can print out a summary of that. Okay, now that we have created our model, let's simulate power. We've simulated, and it looks like we have plenty of power for our original model. So we're going to run a power curve now, and we're going to up here we just had a certain number, 10, 30. Now we're essentially, this is another way of being able to expand things, 20 and 80. We're essentially making a new linear model object. So I'm going to run that, and then run this. And you see here, we set progress to false, so there's less of those bars telling we're simulating. If there's some issues, they often still pop up here, but this might take a while, so we'll come back. We finished up here and plotted the curve here. We see that a number of levels fall between about 40 and 60 when it comes to kind of target sample size. Okay, so let's try now against number of items. So we're going to do a power curve across item. Different breaks because we had a different number of items. And again, we'll do progress of false, and we'll plot this. Now that we've run that, we can see we've got our graph plotted here with kind of the sweet spot between around 12 items. Now, in addition to looking at single items, we can look at higher order interactions. So what we're going to do here is create a new item and subject vectors, and then we're going to, instead of condition like we had earlier, I think up here we called just our variable condition, we're just going to C1 is in condition 1 and C2 is condition 2, create those. And we're going to create a frame again, now with 2 conditions. We'll have fixed intercept and slope, and random intercept and slope variance covariance matrix. So essentially just building a model, and residual standard deviation. And then we're going to make our model here. And again, we see here now that our dependent variable is modeled as a function of the interaction between condition 1 and 2, with subject and items still random effects based off that interaction. So we'll run that and then just get a quick summary here. All right, so we got that. That's our formula. And then we'll run power simulation on this. So after 24 minutes, we get this back, and we found that the power for this interaction term of condition 1 and condition 2 is only 17%. So what this shows us is we can actually use simulation to look at not just single terms, but interaction terms. So we'll go back now to the PowerPoint. What we found in our results from example 4 was the power for the base model was actually around 100%, slightly different depending on the simulation seed, which is not surprising because it was based on observed power. And we found from figure 1 that the number of subjects needed was over 55. It's kind of somewhere right in here. While the number of items needed, if we extended by items, was 14. Because like you see 13 would be maybe just a little bit too low, so we'd probably want to go to 14. And we saw that we could also do interaction terms, and we found that the interaction was pretty weak, so we need a lot of samples to get up to the power needed. Okay, we are on to our final example. This is actually environmental data taken from this example here. So the research question they propose is there an effect of estuary modification on the abundance of a marine species? So their model is going to be abundance as a function of temperature and modification and site. So temperature is a continuous effect, fixed effect. Modification is a fixed effect, so that's going to be categorical. And site is a random effect. And that's going to be nested, I think, in modification. So let's get data, create model, run model, and power curve. Here is the data. So you'll need to get the CSV. I believe you can get it from the web link. And let's turn now to R to look at this in action. Here is our data in R. This is the dataset pilot you can get from this website. I'm going to read it in, keep the headers, and then we want to do a little cleanup by changing the variable modification to a factor. And then we're just going to do a quick plot here. You can see here, this is modifications 1, 2, and 3. Actually, I'm going to zoom here. 1, 2, and 3. So these are different categorical factors. And then we have, looks like 6 different sites. And we can just see sort of the variation inherent here. Next, we'll create our model, abundance as a function of temperature modification, and then site as a random effect. And we'll run a summary. There we go. And looking at the fixed effects, looks like they're all significant. So now we're going to see that modification, its estimates are about 1 and about 2. We're actually going to change them to about a tenth or tenfold less, just to lower that effect size. Just so like when we're simulating power, we're simulating lower effect size, since this was a small pilot. So with our pilot study model, we'll simulate. And this shouldn't take too long since we set our number of simulations at 50. Okay, there we go. We got a 62% power, so this is underpowered right now. And then if we use the X tabs here, we can look at the site by modification. All right, so now what we'll do is we'll run a power curve. We saw we don't have high enough power with our modified pilot study model. So we'll do a full model. We'll extend by increasing the number of sites. So let's start with that. Okay, that looks like if we increase that, that gave us enough power. Now let's take a look at if we instead extend by the observations within sites. Okay, and we saw that if we increased here, it looks like that was not as helpful. So far we've learned that more sites gave more power than just more observations within sites. But now let's do that for both sites and observations within sites. And again, that X tab shows us that the number of sites and then the numbers of the observations within sites. And okay, so with this we ran and we have 78 pages. So we got closer to that. So this is pretty quick one, but we saw that if we reduce the number of simulations, we can really get through it a lot quicker. Let's turn back to our PowerPoint. Take a look at example 5 summary. So what we found for the pilot model, it was relatively low power, but again, pilot studies are designed to be underpowered, so not too big of a problem. So when we kind of went for a full model, so increasing our size of the pilot, we increased sites, it was got close to full power that we would need. If we increased within sites, so more observations by site, wasn't as useful. And then if we increased both, we got 74, which is better than just the increased within only, but wasn't quite as good as just simply investing all of our time in or resources in increasing the number of sites. So what this kind of tells us is it was better to increase the number of sites rather than the number of observation within sites. So our model was underpowered, but as you would use this sort of thing to design a full study, we saw that it's best to get more sites than more observations. All right, with that finishes our model. Thank you for joining along. Again, this was supported by DaCCoTA, which is under the NIH award number right here. So please reference us if you found this useful and helpful for your research. I have here a series of resources and references that I use throughout this module. Pick up, as well as, for example 1, if you weren't able to get that data, here is the data in the raw form. You can just copy and paste that.